Okay, so let's very briefly recap last time. So remember, we were looking at the sphere packing problem. We had a bunch of identical spheres. We wanted to pack them into space as densely as possible without overlap. On the other hand, unlike in most physics scenarios, we were doing this in arbitrary dimensions. And I guess there's a sense in which the message of last time was pessimistic, that we really don't understand very much about this. So remember that aside from dimensions 1, 2, 3, 8, and 24, last time all we had were upper and lower bounds. We had lower bounds that the density is greater than or equal to some constant times n times 2 to the minus n. And sometimes we had an extra log n factor. And we had upper bounds. I didn't actually tell you what the bounds were, but the best upper bounds known are that the density is bounded above by about 2 to the minus 0.599 n. This is due to Kabatiansky and Levenstein in 1978. So there is a rather enormous gap between these. And at a mathematical level, we really know very little about what happens in between them. In particular, we don't know, like I said last time, whether we should how much sort of order or symmetry we should expect to have in the optimal packings. We really don't know whether the optimal packings should be some sort of crazy disordered thing or should be, beautiful symmetrical crystals. It's really not clear. And in particular, we don't know whether an exponential improvement is possible in the density. And this, I think, is really the sort of deepest question, at least in high-dimensional sphere packing, that right now all of the techniques we've got are coming in somewhere around 2 to the minus n, if not worse. And if you're going to beat this by an exponential amount, you're going to have to do something radically different. And I really don't know what that should be, but maybe you've got ideas. In any case, that's sort of the current state of things. So if you look in low dimensions, we've got pretty good conjectures. I mean, we'd guessed the answer in 8 and 24 dimensions long before proving it. I would say it would be very shocking if somebody beat the records up through 8 dimensions, say. Between 8 and 24, I would guess we've probably got some pretty good idea of what's going on, but probably not all of the records are correct. Some of them can probably be improved. Beyond 24 dimensions, it's not clear that we have any idea what optimal packings look like. The thing is, this is obviously a matter of opinion, not fact, but I wouldn't be surprised if every guess we have for the optimal sphere packing above 24 dimensions is wrong. In any case, so there's a lot to do here. So let's take a step back and look at how you can describe packings. Yes?
What's the common pattern in the dimensions we don't have an exact solution for?
Oh.
Is it amorphous or is it crystalline or?
We don't know. So the best packings that are known are all Bravais lattices. So these are all pretty well structured. On the other hand, that may just be because we know more about lattices than about disordered packings. So it's really not clear. In a lot of these cases, these are statements more about our ignorance than about the mathematical facts. Other questions? Okay, so let's take a look at how you could describe a sphere packing. So suppose you want to describe one explicitly in low dimensions. So the simplest thing you can do is look at a Bravais lattice. So there's an irritating thing in terminology here which drives people crazy when mathematicians talk with physicists. And that is that in math, let me draw a little table here. I might not have made it big enough. When mathematicians say lattice, physicists say Bravais lattice. And when physicists say lattice, mathematicians say a periodic packing. And so this is basically guaranteed to cause confusion. I'll leave that table up there in case I start slipping into mathematical terminology. I'll try to say Bravais lattice and periodic packing in this talk just because they're the least confusable terms. But on the other hand, if I slip up, please sort of yell at me or something. In any case, so this is the simplest way that you can try to pack things. So here it's just a sort of skewed grid. In other words, we take some basis v1 up to vn for n-dimensional space, and we center the spheres at the integer combinations of these points. So all the vectors, a1, v1 up to an, vn, where the AIs are integers. And this, I'm sure you've all sort of dealt with things like this. So you've got some sort of skewed grid where you've got a fundamental cell spanned by the basis, and you're putting spheres at the vertices of the fundamental cell. So lattices, Bravais lattices, are already surprisingly difficult to handle in high dimensions. The thing is, in 2 or 3 dimensions, these seem like pretty much the simplest things in the world. But in high dimensions, they turn out to be profoundly difficult computationally. If somebody tells you an explicit lattice, even figuring out how dense it is hard. So let's take a look at that. So suppose you want to compute the density of a Bravais lattice. So you need to figure out 2 things. You need to figure out the radius of the sphere, and you need to figure out how many spheres you have per unit volume in space. So the packing radius. The packing radius, what you've got is you want to make the spheres as large as possible without overlap. So you want to expand the radius just to the point where the nearest neighbors are tangent. So what this is going to be is this is going to be half of the minimal vector length. In other words, you look at the shortest vector in your lattice. If, say, this is the origin down here, if this is the nearest lattice point to the origin, you want the packing radius to be half of this distance so that you get a nice tangency. And so in order to compute the density, you need to know how large the spheres are. You also need to know the volume of a fundamental cell. So here, this is just going to be the absolute value of the determinant of your basis matrix. And then to compute the density of your packing, the density is just going to be the volume of a single sphere in your packing divided by the volume of the fundamental cell, because you have 1 sphere for each copy of the fundamental cell. So everything here is pretty nice, except for this minimal vector length part. The thing is, everything else here is easy. We can all do division. We can write down a basis matrix if somebody gives us a basis. We can compute a determinant. We can take an absolute value. We can take half of things. Unfortunately, we're not good at finding short vectors in lattices. And the problem is, somebody might give us a useless lattice basis. The thing is, in low dimensions, you're probably used to the idea that you're going to give a basis consisting of very short vectors of the lattice. If you wanted to give a basis for this lattice, this vector and this vector would probably be the ones you choose. But on the other hand, there's no reason why you should do that. You could give a crazy basis if you wanted to. And in particular, there's no reason why the shortest vectors should occur in the basis you're given. In fact, in high dimensions, it'll be very rare for the shortest vectors to actually occur in your lattice basis. The point is you only got n basis vectors, but you've got an exponential amount of space where shortest vectors should be hiding. So the chances that you happen to have the shortest vectors of the lattice among the n that you were given is really negligible. So the hard part here is actually finding the short vectors given a basis. And it's very hard, given a basis, to produce the short vectors. It's hard even to tell whether you found them or whether there's something else shorter hiding there. So in fact, this turns out to be NP hard to compute. So there's no efficient algorithm for doing it unless P equals NP. So the bad news here is, even if somebody gives you an explicit lattice, you generally aren't going to be able to tell how dense a packing you get from it. And this kicks in surprisingly quickly. The thing is, in practice, computing lattice densities up to 50 dimensions is pretty easy. Computing it in a couple hundred dimensions is really hard. Computing it in 1,000 dimensions is typically beyond all the computational power in the world. And so this is really sad for our ability to do experiments. The thing is, in an ideal world, what I would love to do is play around with lattices in 50,000 dimensions and just start generating them at random and maybe numerically optimizing them and adjusting them and seeing how good a density you can find on the grounds that 50,000 is close enough to infinity that maybe we would learn something about the asymptotics. And the problem is we just can't do it. We can't even manipulate a single lattice in that dimension, let alone numerically optimize it. Yes?
Can we classify those lattices with group theory as we have done in 3 dimensions? And we know the big mosaic cell will be the most symmetric, and it should be kind of invariant under the group. So we are sure about what the shortest is.
Yes, so the question is, can we sort of study high-dimensional lattices using group theory? And the answer is definitely yes, but it's harder than it sounds. So if you're lucky, if you happen to know that your lattice is invariant under a particularly wonderful group, you can often take advantage of those symmetries to massively simplify the calculation. So some lattices are not hard to handle. The thing is, this is hard in the worst case, but if somebody gives you a lattice like Zn, there's nothing terribly difficult about it, partly because it's invariant under such a big group. So if you get lucky, you might have enough symmetries to help you. This won't happen for a generic lattice. And in principle, you can try to classify things by asking, what are all the different groups that can act on lattices? And people have classified this in low dimensions. The problem is the number of groups grows really rapidly. I don't know the asymptotics offhand, but the thing is we're lucky that there just aren't that many groups that act in 2 or 3 dimensions. And the thing is that every group will act in some dimension, and there are a lot of weird groups out there. And not all of them will act on lattices. There are still sort of crystallographic restrictions in high dimensions, but a surprisingly large, painful set of groups acts on high-dimensional lattices. So this is exactly what we'd like to do, given sort of unlimited resources, but on the other hand, you really start to run into trouble once you get into sort of 2-digit numbers of dimensions. Other questions, thoughts? Okay, so lattices are difficult to deal with, and unfortunately, there's no reason to think that lattices are very good in high dimensions. The thing is, in low dimensions, we're used to, 2 or 3 dimensions, where the best packings, the hexagonal packing in 2 dimensions or the face-centered cubic, are lattices. So it's very natural to look at this and think, well, maybe lattices win in every dimension. And we don't know. Nobody knows of any dimension where we can prove lattices don't win. But probably they lose in all but finitely many dimensions. For example, 10 dimensions. I mentioned the best packing last time, which is not a lattice. And lattices don't seem to come anywhere near that density. So in general, the problem with lattices is they're way too constrained. So think about how you specify a lattice, a Brevet lattice. It's specified simply by a basis of Rn. So you've got n vectors, each with n coordinates. So you can specify a Brevet lattice using n squared parameters. In fact, it's more like n squared over 2 once you mod out by sort of rotational symmetry. But whatever, quadratic number of parameters. And the difficulty is, if you think of the amount of space near the origin, the amount of space near the origin is sort of growing exponentially as a function of dimension. So when you try to create a good packing, what you're trying to do is sort of avoid holes. You want to make something that's, let's say, saturated. And the problem is you've got an exponential amount of space where holes can occur, but you've only got a quadratic number of parameters that you can actually adjust. So basically it turns into a game of whack-a-mole in high dimensions, where as soon as you close one hole by adjusting your basis, you've opened up another one on the other side of space. And it seems that you lose. So in fact, one sort of natural conjecture is that in sufficiently large dimensions, there are no saturated Bravais lattice packings. We've got no idea how to prove this. We can't even prove that there's a single dimension where this happens, let alone almost all of them. But on the other hand, basically, there are a lot of things in sphere packing that are controversial, where people have different intuitions. I think people mostly agree about this, that you just aren't going to be able to close all the holes in high-dimensional Bravais lattices. And if this is true, then it sort of forces your lattice to stay away from the optimal density. The thing is, a Bravais lattice that's not saturated is really crummy, because the problem is, once you have a hole here where you can stick another sphere, then you have a hole in every fundamental cell. There's nothing sacred about that hole. You can translate it to any cell you want. So once you've got one hole, every cell will have a hole, and that means you've got as many holes as there actually were spheres, and that means you can double the density. So if this conjecture is true, then it means that you can't possibly do better than within a factor of 2 of the optimal density in high dimensions. In fact, lattices, I would guess, are further away than a factor of 2 from being optimal, but being not saturated would at least sort of, ooh, I better not kick that, would at least sort of force them to stay away from being nearly optimal. So the known packings that are optimal in 1, 2, 3, 8, and 24 dimensions, in each of those cases there actually is a Bravais lattice. So I think the way to think about this is not that Bravais lattices are really good, but rather that Bravais lattices are very simple, and they're pretty much the only things we can handle. In most dimensions, we don't expect it to work out so nicely, though. So what can we do more generally? So more generally, there's no reason why we should restrict our attention to just putting spheres at the vertices of our fundamental cell. In a periodic packing, we've got some underlying Bravais lattice. But instead of just putting spheres at the vertices, we could put some spheres on the inside, we could put it on the sides, and then just repeat this periodically. So basically, you've just got some number of particles per unit cell repeated periodically. An equivalent description of this is a union of translates of a Bravais lattice. In other words, these spheres form one translate, these ones form another translate, these ones form another translate. Each of the spheres in the fundamental cell gives us an entire Bravais lattice worth once we start translating it. So what do we know about periodic packings? So one thing that's not hard to see is that these, at the very least, come arbitrarily close to the optimal density. The thing is, imagine that you have any packing, periodic or not. So maybe some sort of quasi-crystal or amorphous packing or who knows what. So what you can do is imagine taking a really big rectangular chunk of it. And so you take this sort of big chunk and shave off anything that crosses the boundary. So you've sort of shaved the boundary, and now you have only the spheres contained within this big box. And now you just repeat this periodically. So basically, you can take a big box, repeat it periodically, and you get a good approximation to your original packing. It's almost as dense. The only density loss was that you had to shave things that crossed the borders of the box in order to avoid overlap when you repeated it periodically. And if you make the box big enough, the density loss from shaving is negligible. So basically, anything can be approximated periodically. On the other hand, we don't know if you can do better than that. A question that I find really annoying is, do periodic packings achieve the exact optimum? So of course, in 1, 2, 3, 8, and 24 dimensions, we know they do. But in general, we don't know. Yes?
You say if you make the box big enough,
Yep.
then you don't lose any density. But if you have an infinitely big box, isn't that just an amorphous system?
Oh, yeah, so here, the thing is, in the limit, you lose periodicity. But what I'm saying is that you can make it periodic. You don't let the box go straight off to infinity. You take a big box, and you get a periodic packing that closely approximates the density. You take a bigger box, and you get a periodic packing that even more closely approximates it. And basically, you can come as close as you want with periodicity. In the limit, you lose periodicity. And that's the problem with this question. The thing is that you can come arbitrarily close. If you're willing to lose, a fraction of 1%, you can still make it periodic. But we don't know whether periodic packings can actually achieve the exact optimum density.
Well, I guess what you're saying
Yep.
is amorphous packings have much less density than Bravais packings.
They might have higher density than Bravais lattices. Yep. Yeah, so basically we can't rule out the possibility that maybe periodic packings simply don't actually achieve the optimal density. If you want to really optimize it, you better make it in some way amorphous. I don't know whether I believe this or not. I said that this question was not so controversial. This one everybody disagrees about. The thing is, I think it's a matter of how optimistic you are. So one sort of perspective is periodic packings are really flexible. You can use as many spheres as you want. You can make any shape of box. You can do all sorts of things. You have a sort of unlimited ability to tailor it. So why shouldn't you reach the exact density? Why should there be some sort of weird thing that forces you to be aperiodic in some dimensions? So that would suggest that maybe periodic packings do achieve the optimum. I think the sort of pessimistic perspective is to say that there's no reason why they should work. That sort of by default in math, if something doesn't have a good reason for working, it won't. So if there's no reason why periodic packings should achieve the optimum, then probably they don't always. In any case, I don't know what I believe. Yes?
Maybe this is just a repeat of the question that was already asked, but what's the difference between an infinitely large unit cell and an aperiodic system?
So here, in the periodic one, it's got to have a fixed, it's got to have a finite cell. So the thing is, if you take a limit of larger and larger cells, in the limit it's no longer periodic necessarily. So that's exactly what comes up with this question. The thing is, periodic packings with a finite cell can definitely come arbitrarily close to the optimum if you make the cell big enough, but we don't know whether you can actually achieve the exact optimum with a finite cell. And if you let the cell literally become infinite, then it's no longer periodic. Does that answer your question? Or I have a feeling that we're going off on tangents in terms of terminology or something. Oh. Yes?
I'm going to ask something that nobody's asked before.
Yep.
Do we know if there is any amorphous packing or periodic packing that have higher density than a Bravais lattice?
So we don't know. So nobody has been able to prove this. In 10 dimensions, there's a periodic packing, the best packing, so the best packing with a capital B, also the best with a lowercase b at R10, is periodic. It's got 40 particles per cell. And they're based on a sort of binary error correcting code in a way where when you first see it written down explicitly, you look at it and you say, there's no way that can possibly be the best thing in 10 dimensions. But nobody's ever been able to beat it. And it's about 8% denser than any known Bravais lattice in 10 dimensions. So we can't rule out the possibility that there are better Brevet lattices than we've been able to find. Nobody can prove we found the best Brevet lattice so far. But on the other hand, I'm pretty sure we know the best Brevet lattice, and it's sort of noticeably less dense than the best packing. Yep.
How would you fill up a unit cell?
How do you do it in practice?
Yes.
That's a good question. So, in general, this is not an easy thing. The thing is, in low dimensions, you just draw a picture and start plopping things in and hope it works. But on the other hand, that fails starting in 4 dimensions unless you've got better high-dimensional visualization abilities than I do. And in general, it's hard to fill up a cell. So one possibility is you sort of guess the answer based on symmetry or something like that, which only works if you're very lucky or very clever. Another possibility is you do some numerical optimization where you make some sort of initial guess and start moving things around and see if you can optimize it and fit more in. Another possibility is you do something like what Best did, where you come up with some sort of conceptual scheme like, I'm going to sort of determine the locations based on some error-correcting code or something like that. I mean, that just reduces the question to where did the error-correcting code come from? But, in fact, it came from a computer search. But basically, the answer is we really don't know. Part of the problem is if you look at the best packing, 40 particles per cell, I mean, by physics simulation standards, it's not that many, but by mathematical standards, that's a pretty high number of particles. The thing is, I feel like a Brevet lattice, I can't visualize it in high dimensions, but I can sort of squint my eyes and imagine that the 3-dimensional pictures in my head are higher dimensions. But on the other hand, I can't really imagine 40 particles per cell because I lose track of particles. The thing is, in my head, sort of 40 particles is, an indeterminately large number all sort of milling around. So basically, I think part of the reason why we're not good at finding sphere packings in high dimensions is nobody has a good answer to your question. But we need more computation and more theory here. Yes?
Do I understand correctly that the cell here in the 40 particles per cell,
Yep.
the length, any one dimension of that cell is like 1 particle diameter? Or how big is that cell relative?
I think it's a little bit larger than that. I would have to look it up to be sure, though.
Because when I think 40
Yep.
particles in a cell, I'm like, okay, big cell, 40 particles, there it is.
Yep.
It's like, no, it's not like that.
Yeah, it's slightly bigger than the sort of 1 particle length on each side, I think. But on the other hand, it's a pretty compact cell.
So everybody has a neighbor, like everybody's their own neighbor, or one more neighbor to come around to the.
Yeah, I think that each of them has. I've forgotten how many neighbors they have, but it's well into the hundreds. And so the thing is, a lot of packings like this, especially ones with big symmetry groups, have tons of neighbors. That if you look at the sort of isostatic condition, that would suggest that in order to achieve jamming, you should have 20 neighbors for each particle. But in fact, I think in the best packing, you have like 300 or 400. Yes?
What's the randomness? So the 40 particles in the first cell are randomly placed. How are you do like? Is there a G of R? Is there a structure factor? Is there any measure of the shape of the 4 particles that are randomly placed in the cell?
I don't know. I haven't done a lot of calculations with the best packing. It's all very explicit. You can write down the error-correcting code and sort of write down explicit coordinates for everything. But I've never tried computing sort of pair correlation functions or anything like that. So I don't really know what it looks like. I'd be curious, though. Basically, the best packing, to be honest, I've sort of always viewed it as a cautionary example that, things can be more complicated than you think. And the thing is, nothing like this has been found below 10 dimensions, and not that many things like it above 10 dimensions either. And so I think it's sort of hinting at a broader theory, but right now, it's kind of an isolated example showing things can just be crazier than you would think looking at simpler cases. Yes?
Are there periodic packings in higher dimensions than 10 that beat Brevet lattices?
Yes. The thing is that, so at the very least, these are known in 18, 20, 22 dimensions. So you might wonder, what about the odd dimensions? And the answer is these were found by a sort of coding theory-based construction that works better in even dimensions than odd dimensions. And I really don't know whether that means there's actually a difference between even and odd dimensions, or whether it means people just don't have enough good ideas yet to do the odd cases. In any case, there were a number of sort of higher dimensional analogs of this known, but our knowledge is frustratingly incomplete. And I can't really believe that 19 dimensions behaves so radically different from 18 and 20. In 19 dimensions, a Brevet lattice is the best we know, but nobody's been able to beat it yet. Do you have a question?
So, am I correct in thinking that, suppose I want to find the maximum density achievable by a Brevet lattice, not all the time in the world, and I'm going to do that in a particular dimension. Requiring that all the integer linear combinations, the basis vectors, have a given length.
Yep.
Those are all convex constraints, but the problem is there are many, many of them, essentially an infinite number.
Yep.
And the upper bound on the number of them that actually matter in the convex body is what? Exponential density, or in the dimension, or super exponential somehow, or?
Yeah, so the question is, could you solve the Brevet lattice problem exactly? And the answer is yes, that what you can do is you can look at the Gram matrix of your basis, and you get basically linear constraints on the Gram matrix for each set of AIs saying that your vector can't be too small. You say fix the determinant to be 1, and you've got a sort of positive semi-definite constraint on this. And then you've got some convex optimization problem. It's in principle infinite, but you can reduce it to a finite problem under the action of GLNZ, sort of change of basis. But you're exactly right that the problem is you reduce it to an exponentially large problem. And so you can solve this in principle. People have worked out the best Brevet lattice up to 8 dimensions by solving this problem. In 9 dimensions, it hasn't worked out yet. That basically what you end up doing is having some massive polytope and basically trying to find all the vertices of it. And the number of vertices seems to grow dramatically. I think it's 35 modulo the group action in 7 dimensions, about 2,000 in 8 dimensions, and people have found about 500,000 so far in 9 dimensions, but haven't found them all yet. And
why do we need to find them all if you're saying it's a linear problem on the Gram matrix?
So the thing is that you don't need to find them all in principle, but on the other hand, right now, the only way people have found to even reconstruct this is basically traversing the whole thing. And it's possible that there are better algorithms that people should be applying. Right now, my feeling is 9 dimensions, somebody's going to do it within our lifetime. That 10 dimensions, I hope somebody does it within our lifetime, but I'm not sure. And I doubt that we'll get much higher than that without better ideas. Other questions, thoughts? Yep?
Did you say that in 19 dimensions the best non-packing was Brevet lattice?
Yes.
But you did also say that Brevet lattice could not be saturated.
Probably they can't be saturated in high dimensions, but high would be at least in the hundreds here, I think. So, yeah, the thing is that there's a lattice in 72 dimensions that I'm almost sure is saturated. And my guess is the cutoff point is probably in the hundreds. Okay, let's see. So I want to do 2 things. One thing, I want to take a quick digression to something that's not really about packing, but that I think is a lot of fun. So let's think about this computational problem of finding short vectors in lattices. So I said that finding the shortest non-zero vector in a given lattice, if you're given a lattice basis, is NP hard. So there's very little hope that we can solve it exactly. In fact, it's NP hard to approximate it within a certain factor. On the other hand, we've still got lattice basis reduction algorithms which do a pretty good job of giving you short vectors. The thing is, they won't give you the shortest vector. They'll give you a vector that's optimal to within a slightly sub-exponential factor. That sounds terrible, but they actually work surprisingly well in practice. So I wanted to say two things about this problem. Basically, whenever you run across a hard computational problem, there are two questions that you should ask yourself. One is, can you take advantage of the difficulty to do something like cryptography? The thing is, cryptographers are a sort of weird bunch because they get very excited about computational difficulty, because without computational difficulty, you're never going to actually have codes that are hard to break. And so it turns out the fact that this problem is hard for lattices might end up basically saving the world. I'm exaggerating, but only slightly. The thing is, if you think about cryptography, public key cryptography, don't worry if you don't know exactly what this is, I don't want to get into too much of a digression, is really important for modern technology, the internet, let's say. And we would really like this not to be breakable. And the problem is, people have proposed a lot of different public key crypto systems over the past 30 years, and most of them are terrible. The thing is, if you sort of select a random, public key crypto system proposal from the literature, you typically get something that's sort of a crackpot proposal that's easy to break if you know a little bit more than the authors. The thing about cryptography is it's easy to sort of propose systems for encrypting that you can't break, but that maybe other people can. So basically, the only public key crypto systems that have ever really withstood scrutiny are based on luck. The thing is, there are a handful of mathematical problems that look like they're particularly suitable for building cryptography. So for example, one of these problems is factoring. Another closely related one is the discrete log problem. There are several others that are a little bit less famous and well-studied. But another category is lattices. So the problem is, if we want to do cryptography, we've only got a handful of problems that look like they really work and that are well studied enough that the chances of somebody breaking them tomorrow are slim. And there's a problem with most of them. And that is that quantum computers can break most of them. In particular, quantum computers, if we could build one, could factor numbers efficiently into primes, they could compute discrete logs. They basically screw up a lot of things. So the big danger with quantum computers is that they could ruin a lot of existing cryptography. It's a little bit sad because quantum computers, frankly, don't seem like they're good for very much. They're great for simulating quantum systems. If you want to do that, they could be amazing. They can do a few things like, some square root speedups and database searches and stuff like that. But frankly, the thing that they're most useful for is making cryptographers unhappy. So the big danger is, if you had a working quantum computer, you could break a lot of cryptography. On the other hand, as far as we know, quantum computers can't actually find short vectors in lattices. So basically, this problem not only appears to be hard for classical computers, but in fact, nobody knows how to do it on quantum computers. When I say nobody knows, I mean nobody knows in unclassified work. Who knows what the National Security Agency knows? But basically, there's been a lot of interest in using lattices for cryptography, partly because it's one of the few sort of realistic hopes we've got for doing things in a way that possibly can't be broken by a quantum computer. So I wanted to take just a couple of minutes and describe one way that you can try to do cryptography based on a lattice. So what I'll describe is a cryptosystem due to Goldrake, Goldwasser, and Halevi. And I'll put a don't use over here in the corner of the board. The thing is, this was proposed around 1997 or 98, and a couple of years later, a cryptographer named Fong Wen found attacks on this. They don't rule it out absolutely, but they mean if you want to use this, you're going to have to use really huge parameters, and basically don't try using this. But this will at least give you a sort of flavor for how you could encode messages using packings. So the idea is, I want to create a public key system. In other words, I want to set things up so I'm going to announce some information to the world. I'm going to announce to the world what's called a public key. So I'm going to tell everybody in the world my public key. I'm going to publish it. And anybody who knows my public key will be able to send me an encrypted message in such a way that I can read it, because I've got the private key. So basically, this can be used for decryption. The public key can be used for encryption, but you can't determine the private key efficiently from the public key. So basically, we're going to set things up so that anybody can send me a message, but only I can read it. So what is the public key going to be? What it's going to be is it's going to be a Brevet lattice basis. So basically, I'm going to announce to the world a basis for some lattice. And what's my private information? What I'm going to keep secret is how I generated this. What I'm going to keep secret is there's going to be a secret nearly orthogonal basis. So what's the point? So by an orthogonal basis, I just mean, four, at right angles. So if you literally had an orthogonal basis, it would be a really stupid lattice, and you would never use it for this. So the basis is not going to be literally orthogonal. It's going to be nearly orthogonal. So I'm going to take something that's almost at right angles, but not quite, a little bit perturbed. And I'm going to keep the sort of, I'm going to keep this basis secret. So basically, secretly, I'm going to have a sort of hidden basis that shows that my Brevet lattice is not actually so weird. Everything's almost at right angles. But I'm never going to tell anybody else my secret basis. What I'm going to do is I'm going to totally screw it up. I'm going to start adding multiples here and there, doing change of basis, until I get some really horrible, ugly basis that doesn't look at all orthogonal. And I'm going to tell the world some crazy basis. And my hope is that if I tell the world a crazy basis, that if it's in a 1,000-dimensional space, say, that nobody will be able to reconstruct the nearly orthogonal basis. So now, how does the system work? So how do I send a message using this Brevet lattice? So if I have a message I want to encrypt, so first of all, I'm going to turn the message into a lattice point. There's nothing secret about this. I'm just going to, write it out in binary or something and take a combination of the lattice basis. Somehow I'm going to turn the message into a point in the lattice. So how am I going to encrypt? The way I'm going to encrypt is I'm going to perturb the point off of the lattice. So here's the picture. So the message is going to be some lattice point. And the way I'm going to encrypt things is I'm going to add random noise, and I'm going to turn it into a nearby point. So the message is a point on the grid itself, and the encryption is going to be a point in space, not on the lattice, but kind of nearby. So in low dimensions, this will be an unbelievably stupid cryptosystem. The thing is, in 2 dimensions, anybody with half a brain would draw a picture and say, look, I just drew this grid. Here's the encrypted point. Let's look at the nearest lattice point. That must be the decryption. So if you want to decrypt, all you do is you find the nearest lattice point, and then you're done. Yes?
How do they know what the lattice is?
The lattice has been publicly announced, so everybody knows what the lattice is. So here's the problem. The thing is, anybody can encrypt because they know the lattice. And anybody can add a little bit of random noise to push the point off the lattice slightly. But the problem is, how do you get back to the lattice? In order to get back to the lattice, you have to be able to solve the problem of what is the closest lattice point to this perturbed one. And that's the sort of thing where if you know the private key, if you know a secret nearly orthogonal basis, then that gives you enough structure that it turns out you can solve this problem. Basically, if your basis is nearly orthogonal, you can reconstruct the lattice point by just projecting into each coordinate with respect to that basis. So if you know enough about the structure of the lattice, you can invert this. But the problem is if somebody doesn't know that, if all they know is this crazy, ugly basis, then, you know, somebody gave you 1,000 vectors in 1,000 dimensions. Somebody gave you some weird point in space and said, what integer linear combination of these vectors is closest to that point? You've got no idea. So,
Can one visualize
yep.
in 2D or 3D what an ugly basis would look like?
Yeah, so the thing is, a nice basis might look something like this. An ugly basis might be, you know, one thing that's way out here, another one that's way out there, but just some pair of vectors that spans the same lattice, but that's sort of greatly distorted. So the thing is, 2 dimensions is a little bit misleading because 2-dimensional lattice basis reduction is easy. If somebody gives you a crazy basis, it's easy to simplify it and sort of return it to something like this. So in 2 dimensions, the computational problem just isn't that hard. But in high dimensions, as far as we know, if somebody gives you a horrible basis, there's no way of telling whether there's a nice basis they could have given you instead. Yes?
So if I actually carry out Gram-Smith and I actually get an orthogonal basis, does it help?
So here's the problem. Gram-Schmidt will give you an orthogonal basis, but it won't preserve the lattice. The thing is, when you do Gram-Schmidt, you're typically sort of adding and subtracting sort of non-integer multiples of things. And so the thing is, you can take any basis and you can make it orthogonal by Gram-Schmidt, but now you've screwed up the lattice. So basically, Gram-Schmidt is exactly what you would like to do if it preserved the lattice, but unfortunately it doesn't. So for example, if you just took this basis, if you did Gram-Schmidt, it would turn it into that, but that basis isn't even in the lattice to begin with. Yes?
So is this somehow similar to just finding the distance, finding the nearest lattice point to the encrypted message?
Exactly. So here, the hard computational problem is, what is the nearest lattice point to a given point in space?
To do that, you have to compute the distance of every single lattice point.
There are slightly better algorithms than that, but yeah, that's essentially the issue, that there are exponentially many lattice points that could be the closest, and you don't even know which one to try.
Clarification.
Yep.
So you mean the secret nearly orthogonal basis span the exact same lattice?
Exactly, for the same lattice, yep. Sorry, yeah, let me clarify that. So the sort of secret here is that you didn't use an arbitrary lattice. You used a lattice that's actually a lot simpler than it looked, but you didn't let anyone else in on the secret. So Fong Wen's attack on this basically showed that it's easier to detect a secret nearly orthogonal basis than people thought it was. But there are sort of fancier schemes than this that are more secure.
Can you say, in this example,
Yep.
what's a new orthogonal lattice? Is it the simplest, the basic?
Exactly. So here, basically, the problem is, if you have a lattice basis, how do you go to the nearest lattice point from some point off the lattice? So what you might hope to do is to just sort of round off each coordinate. And that amounts to sort of projecting onto this line, projecting onto this line. So basically, if your lattice basis is good enough, if things are close enough to right angles, you can do it coordinate by coordinate and it just works. On the other hand, if you have a horrible basis, then if you try to do it coordinate by coordinate, you'll just screw it up.
But would you say that's good enough? Because the elementary
This lattice basis is probably good enough, the one I drew. Yep?
Does the strength of the encryption depend on the amount of noise that you have?
Yeah, so there are a bunch of parameters here. There's the question of how high the dimension is, how close to orthogonal you should be, how much you screwed up the basis, how much noise you add. So you've got to choose all these parameters in a way that you think makes it hard. The thing is, if your encryption is too close to the lattice, then it'll be really easy. If it's too far away, it might end up closer to another lattice point. Yep?
What would the words nearly orthogonal mean? Is there an actual limitation that there are more perfectly orthogonal bases of this sort, or it is a requirement of the algorithm because perfectly orthogonal bases can be easily wrong?
Yeah, so here it's a requirement for security. The thing is, if it were exactly orthogonal, everything would still work, but it turns out it's easy to find an exactly orthogonal basis. So basically, the nearly is sort of a compromise. In an ideal world, you would delete that, but then the crypto system is no longer secure. Yes?
Is this the encryption that's used? Is this used commercially?
Nope. So there are two issues. One is, in practice, people would use sort of more sophisticated things, similar in spirit, but more secure. And the other big issue is, if you want to use this in practice, you've got to announce to the world this public key. And the problem is, the public key is going to be annoyingly large. The thing is, if you want this to be secure, you'll at least have a couple hundred dimensional basis, which if you've got sort of 200 dimensions, then you'll be giving 40,000 numbers to describe your basis. And each of those numbers will probably be pretty big. And so you'll get a fairly massive public key. And in practice, people are very reluctant to use this. The thing is, in practice, people have really wanted to streamline their cryptography and make everything as small and efficient as possible, partly because, you know, mobile devices and embedded processors and whatnot, you want them to be able to handle all your cryptography too. And in particular, that means you want to make everything as small and efficient as possible. So basically, before quantum computers, nobody really wanted to use lattices because they looked at this and said, you've got public keys, 1,000 or 10,000 times larger than other systems. And so basically, the sort of security world has been dragged kicking and screaming towards lattices by quantum computers, but we might have no choice. Okay, so I want to say one other thing just for fun before talking about density bounds, and that is a sort of positive application of lattice basis reduction. The thing is that here we've got an application based on the fact that it's really hard to do this. But let me talk about something fun that you can do using existing algorithms. So first of all, how should we think about the NP hardness here? So NP hardness, it doesn't just mean that your problem is hard if P is not equal to NP. It really means your problem is computationally universal, at least within NP. That basically what this is saying is that finding short vectors in lattices is a flexible enough problem that you can embed lots of other problems in it. And in fact, some things can be embedded in particularly clean ways. So here's a problem that I really enjoy, and that's recognizing numbers. So imagine that somebody gives you the number minus 7.82679932376740292997644895, and asks you what you think that number is. And if anybody actually recognizes the number, I'll know that you were sort of cheating by looking up my PCMI notes, because I don't think any human being can actually recognize this. But this is the sort of problem that comes up surprisingly often in numerical work, that you've numerically computed something, you suspect this isn't just a random number, but it's actually got some structure, and you would like to know what it might actually be.
Do you mean recognize in terms of some irrational?
Exactly. So for example, can you find a closed form for this? And of course, it's not a well-posed problem. The thing is, we don't know what the remaining digits are. There are infinitely many numbers. Anything with this decimal expansion then does whatever it wants could be a valid answer. On the other hand, we would really like the simplest answer. So for comparison, imagine if somebody asked you to recognize the number 0.1345345345345, etc. So again, this is not well posed. There are infinitely many numbers, but any reasonable person, I think, would guess that this is a 10 plus 345 over 9990. That basically the 345 is probably repeating, making this a rational number. So basically the question is, can you guess what this number alpha is? And in order to have any hope, we'd better sort of narrow it down to some family. And let's look in particular at algebraic numbers. In other words, roots of polynomial equations with integer coefficients. So for example, the square root of 2 is a root of x squared minus 2. So we'd like to know, is alpha an algebraic number? So this might seem like, even by the standards of my talks here, that this is sort of far from practicality. It turns out that identifying algebraic numbers is useful in the real world. It's one of the few things that I've done at Microsoft that's actually been a sort of practical contribution to the company. I didn't come up with this algorithm, I just applied it, I should say. But it turns out that in certain sorts of cryptosystems, in particular based on hyperelliptic curves, when you want to choose parameters, you end up with really nasty computational problems where the best known algorithm for solving them is you do a really high precision floating point calculation to compute a certain theta series. The answer is guaranteed to be an algebraic number. Then you apply this sort of algorithm to recognize the algebraic number. You reduce it mod prime and you keep on going. The details aren't important. But the point is that there exist cases where, for practical real-world concerns, you actually want to identify algebraic numbers. So how can you do this? So one of the things I love about this is basically this will amount to computing the density of a Brevet lattice packing. So let me tell you a lattice that corresponds to this number. So I'm going to use the following basis. First of all, I'm going to take a really big constant. Let's say 10 to the 20th. Basically, this constant is chosen based on how many digits I wrote up there. Let's not worry about it. It's just a big number. And I'm going to take the following basis. So my basis is going to consist of 1, 0, 0, 0, 0, 0, C, 0, 1, 0, 0, 0, 0, C times alpha, 0, 0, 1, 0, 0, 0, C alpha squared, etc. In other words, we've got an identity matrix, the one sort of marching along the diagonal, and we've got C times powers of alpha. So we've written down the spaces. So the question is, what's the Brevet lattice you get from this basis? So the Brevet lattice is, you're going to take integer combinations, A0 times this, plus A1 times that, plus A2 times that. So what do you get for a lattice vector? So I've chosen this lattice. So the basis is very simple. The identity matrix part is totally boring. You get an A0 in the first part. You get an A1 up to A5 at the end. And then you get C times A0 plus A1 alpha plus A2 alpha squared plus up to A5 alpha to the fifth. So basically, I've chosen the basis in such a way that the first 6 coordinates simply tell you what coefficients you're adding up, and the last coordinate tells you a big constant times a polynomial in alpha. So now what do? Now what we want to do is find a short vector, a short non-zero vector. We probably won't be able to find the shortest vector, but I said there were good lattice basis reduction algorithms. If you apply them here, they will find a pretty short vector. So what does it mean to have a short vector? What it means is these coefficients have better be pretty small. In order to make this short, the coefficients AI can't be too big. On the other hand, this polynomial in alpha has to be really tiny. Because remember, we're multiplying it by C, which is huge. So in order to keep from getting a large vector, the thing that we're multiplying by a gigantic number had better be very small. In other words, finding a short vector in this lattice amounts to finding small coefficients for a polynomial that nearly gives 0 when you plug in alpha. So in fact, if you use, your favorite computer algebra system and just type in this basis and say, apply lattice basis reduction, tell me a short vector, Mathematica or Maple or something like that will simply tell you an answer of 71 minus 5, 12, minus 19, 13, 2, 0.000004, blah, blah, blah. So what is that telling us? What that's telling us is these coefficients, if we make a polynomial in alpha out of them, give nearly 0. In other words, it's telling us that 71 minus 5 alpha plus 12 alpha squared minus 19 alpha cubed plus 13 alpha to the fourth plus 2 alpha to the fifth is approximately 0. And in fact, that's exactly the equation that I used to generate alpha. So basically, you can use this to invert solving polynomial equations. Instead of given a polynomial equation, figure out what the roots are, you can use this to, given a root, figure out what the simplest polynomial equation that you can find is that has that as an approximate root. Yes?
Then what was the point of setting C to a very large number?
So here, the point of making C big is to force this to be small. The problem is that you want to pick small coefficients, but you want this polynomial value to be really, really near to 0. That having coefficients that get it, if the polynomial came out to, 0.1 or something, then you would say, hey, that wasn't very close to 0. This wasn't really an approximate root. So the point here of multiplying it by C is in order to force this to be really tiny in order to get a short vector.
And that means you need precision of about 1 over C in the original memory.
Exactly. So the thing is, the choice of C is, if C is too small, then you're not forcing this to be close enough to 0. If C is too big, you're forcing it to be too close to 0, which is unrealistic if you didn't know alpha accurately enough in the first place.
So
Yep.
Very specific question. In the example, you have 7 your basis, I mean, your space has dimension 7, right?
That's a good point.
I mean, I'm missing one vector in the basis.
This is, okay, so actually this is not quite consistent with what I was doing earlier. This is a basis for a 6-dimensional lattice embedded in 7 dimensions. So you're totally right, yeah. The thing is that...
You embed your lattice in n+1.
Exactly. And that's fine. The thing is, there's no reason why you can't embed it in a higher dimensional space. But yeah, sorry, I was sort of skipping over that detail. Yep.
So to reconstruct this equation, do you have to know the degree of the polynomial?
Yeah, so here, in order to set up the lattice, you're sort of choosing the degree. Here I was choosing degree 5, but you could choose whatever you want. So if you wanted to look for a degree 21, that would just be a higher dimensional lattice. In practice, you run into computational problems. If you wanted to choose degree 1000, you probably wouldn't be able to find the short vector, since that's way too high a dimension for your lattice. But at least for sort of moderate degrees. The other thing is, there's nothing sacred here about algebraic numbers. The thing is, I set this up. What this is really doing is it's looking to try to find a combination of 1 alpha, alpha squared, up to alpha to the 5th that's nearly 0. But there's no reason why you have to use powers of alpha. If you wanted to try to find a combination of 1 alpha, e, and pi that was nearly 0, you could do that too. So basically, you can use this to find linear relations between any numbers you want. In any case, I can't say this is terribly important for the theory of packing, but I really enjoy the fact that this problem, which at first glance seems to have nothing whatsoever to do with sphere packing, recognizing this number amounts to computing the density of a certain packing of 6 dimensions. Okay, so we've got about 25 minutes left. And one thing that's still on the agenda that I think I promised last time is to say something about how you prove density upper bounds. So far, all I've done is describe sort of qualitatively what lattices look like and where some of them come from. But I haven't told you anything about how you prove bounds and what you can achieve. So let's see if we can do the very quick version of this. Yes? Why do you have to do what?
Very high dimensions. You will just set amplitude at the time.
Sorry, I'm missing. What was your question? What do you have to go to high dimensions? Why don't you do what?
Set 1 digit at a time.
In this crypto system, or?
In any.
So, here, the issue with high dimensions is that if your dimension is too low, then you can find the nearest lattice point and you can break it. So you can do this in any dimension you want. The only reason you need high dimensions is for security purposes, because it's not secure in low dimensions. But on the other hand, it has nothing to do with the sort of functionality of the algorithm, only the question of whether you can break it. Okay. So where do upper bounds come from? So remember that we had 1, 2, 3, 8, and 24 dimensions. So let me set 1, 2, and 3 aside. The thing is, 1 dimension is trivial, 2 is classical, and 3 is hard. But where do 8 and 24 come from? And also remember that we had this density bound due to Kabatiansky and Levenstein of 2 to the minus 0.599n in high dimensions. So it turns out exactly the same technique that proves this density bound also gives 8 and 24 dimensions. And we ought to be able to do much better. We just don't know how. So what this technique is based on is it's all using the pair correlation function. So remember, the pair correlation function just measures how many times each pairwise distance occurs. So the question is, how do you turn this into bounds? So let me give you the sort of physics jargon first, and then I'll sort of explain in more detail how the calculations work. So remember that if you do a Fourier transform of your pair correlation function, you get what's called the structure factor of your packing. And the structure factor is non-negative. So basically, the non-negativity of the structure factor puts a sort of strong constraint on the pair correlation function. So the basic question that you ask then is, what sort of pair correlation functions could you have subject to having a non-negative structure factor? Yes?
Help me out here, it's been a long time. You mean that it's non-negative for all frequency vectors?
Exactly, yep. So it's a function that's greater than or equal to 0 point-wise everywhere. Yeah, so basically the question is, how good a packing can you get subject to this constraint? And so remember that the pair correlation function determines the packing density. The thing is, the pair correlation function, first of all, if you look at this over all of space, it tells you how many particles you have per unit volume in space. And the pair correlation function also tells you the distances that occur between between particles. So it tells you the packing radius. So basically, the pair correlation function determines the packing density. So then the question is, how good a pair correlation function can you find? And what makes these bounds work is you can show that if the packing density is too high, then the pair correlation function cannot possibly lead to a non-negative structure factor. So basically, this sort of constraint gives you asymptotic bounds in high dimensions, and it also exactly solves the problem in 8 and 24 dimensions, which is really crazy. The thing is that one way of thinking about this is it's saying the pair correlation function in 8 and 24 dimensions secretly knows everything about these objects. That in particular, the pair correlation function alone encodes enough information to prove that these packings, the E8 packing in 8 dimensions and the Leech lattice in 24 dimensions, are optimal. So this doesn't happen in 3 dimensions. As far as we know, it doesn't happen in any other dimensions above 3 except for 8 and 24. And, but somehow the pair correlation function is miraculously powerful in these cases. So I'll take a step back and describe in a little bit more detail how this works. But I want to say one thing first, which I think is really weird. So you could ask, which dimensions does this sort of argument work in? So I said it worked in 8 and 24 to solve this exactly. It also works in 1 dimension. In 1 dimension, it's not very exciting. Nobody's ever been thrilled to learn what the densest 1-dimensional packing is. But in fact, the pair correlation function tells you everything you need to know. The thing that's sort of embarrassing for the theory right now is it might work in 2 dimensions as well. The thing is, numerically, if you try applying these methods, numerically it seems to work in 1, 2, 8, and 24 dimensions. And we can prove it in 8 and 24 dimensions. We can't prove it in 2 dimensions. Of course, we know what the densest packing is by much more elementary means. But the technique that works in 8 and 24 dimensions seems to work in 2 as well. We just can't prove it. And this is something really weird is going on here that I find difficult to understand or explain. The thing is, for years, I would tell people that it seems to work in 2, 8, and 24 dimensions. And the fact that we can't do it in 2 dimensions is encouraging, because how hard can 2 be? Sooner or later, someone's going to figure out how to optimize this method in 2 dimensions. And once we can do 2, then maybe we'll be able to do these much deeper 8 and 24. And instead, somehow the way it worked out is now we can solve 8 and 24 this way, but we can't even verify that the technique works in 2 dimensions. So something weird is going on. Was a question?
That in 8 and 24, I guess in 2, that there are points at which the structure factor dips to exactly 0?
Yep. In fact, the structure factor will consist of delta functions, so it'll be not literally a function, but a distribution. Yep.
I don't quite understand the condition on the structure function being positive.
Okay, yeah. So let's take a step back, and I'll tell you in more detail how these techniques work. So I'm not actually going to describe it in terms of the structure factor because basically I've never been super happy with this language. I'll describe it in different terms, but it'll be morally equivalent to this.
Are you considering non-periodic structures as well?
Exactly. So this is for all possible packings. So you look at sort of arbitrary pair correlation functions and ask how high a packing density can you have subject to these inequalities.
But if the structure function is negative,
Yep.
what does that mean?
So that means, so the thing is, imagine somebody gives you a pair correlation function and says, hey, look, here's a pair correlation function for a packing. So one way you could disprove this would be you compute the structure factor and it turns out to be negative, and you say, no way, that's an actual packing. You've screwed something up that can't be the right pair correlation function because, hey, the structure factor dipped below 0. So basically, this puts a constraint on what the pair correlation functions could look like. And the way these theorems work is basically you show that it's impossible to get a higher density without forcing the structure factor to be negative. And that means no packing can achieve a higher density.
Is that an assumption? Is there an assumption that this is hard disks?
Exactly. So this is only for sphere packing.
Right.
You can also do this for other sorts of soft potentials, but that's a little bit different.
So you say you take hard objects,
Yep.
spheres, and if they don't overlap, then structure factor has to be positive, like I said, no?
Exactly. Yep.
The factor is the density square. So it has to be
Square.
whatever is the factor.
No, it's the square of the density fluctuation.
Rough case, absolute value square.
Okay, let's see. We've got, what do we have? 12 minutes. Let me see. Trying to compress this. Okay, so let me tell you a theorem, and it'll be morally equivalent to this. It'll look a little bit different, but I'll sort of explain what's going on in a moment. So let me just remind you what the Fourier transform is. So if we have a function of n variables, so remember that the Fourier transform is you just integrate it against a complex exponential. And the only question is, where do you put the 2 pi's? And I'm going to put the 2 pi's there where they belong. But if you like them somewhere else, then you'll have to adjust all my formulas. Okay, so we've got this Fourier transform. So for the rest of today, let's assume that f is a nice function. The thing is, I don't want to sort of clutter things up with integrability hypotheses and whatever. I'll say things, and they're all true for any sort of sufficiently good function, unless you're sort of going around looking for counterexamples. So the techniques that we'll use are based on a really wonderful duality theorem called Poisson summation. So what does it say? So what it says is, let's imagine we've got a Brevet lattice lambda in Rn. And we've got a nice function f. You know, it's smooth enough and decays enough at infinity, whatever. So the question is, what happens if we sum our function over the lattice? So in general, there's no hope of getting a sort of simple answer for this, but Poisson summation gives you a beautiful duality that says summing f over the lattice is practically the same as summing the Fourier transform over a closely related lattice called the dual lattice. So basically, you've got this. The only difference is, I'll write it like this: 1 over the volume of the quotient torus. This is the volume of a fundamental cell. So basically, summing a function over a lattice is the same as summing the Fourier transform over the dual lattice up to a factor of 1 over the volume of the fundamental cell. So here, lambda star is the so-called dual lattice the quickest way to well, maybe not the quickest way, the simplest way to describe what it is take any basis of lambda, and now take the dual basis in the linear algebra sense with respect to the sort of dot product, and that's a basis for the dual lattice. In any case, we won't really need to know what it is. If you're not sort of familiar with this, just think of it as some lattice associated with lambda. So basically, you can think of Poisson summation as saying, you know, what transformation of lattices corresponds to the Fourier transform for functions? There is such a transformation called the dual lattice. So the thing I feel a little bit bad about is presenting Poisson summation this way, because this statement is a very beautiful sort of duality, but it looks very mysterious. The first time I saw this, I thought, you know, wow, you know, that must be a really deep and difficult fact to understand, because the left and right sides have no apparent connection to each other. It turns out there's a very sort of simple reason to see why this is true. If you want to see what it is, though, look at my PCMI notes, because otherwise we're totally going to run out of time. But basically, these proof techniques are all going to be based on Poisson summation here. So let me tell you about a bound that Noah Melkes and I proved in 2003. So what we proved is a bound that says if somebody gives you a function f with certain good inequalities, you can get a sphere packing bound. So imagine you have a function of n variables, a sort of nice function, well enough behaved, and imagine that it has the following properties. F is non-positive whenever you go out sufficiently far, say radius at least 2. Maybe I'll write it like this. Imagine that f hat is non-negative everywhere. And imagine, in particular, that it's positive at the origin. So why you should want a function with these inequalities will become clear in a couple of minutes. But let's imagine that you have one. So somebody gives you an auxiliary function f, where f and f hat sort of behave oppositely. F is non-positive a lot, and f hat is non-negative everywhere. So you can think of this as sort of a paradoxical function that's driving f and f hat in opposite directions. Then what you can conclude is the sphere packing density in Rn is bounded above by a certain constant, which you'll recognize from the sphere volume last time, times f of 0 divided by f hat of 0. So basically, you can think of this function as sort of a certificate for a sphere packing bound. If you can find a function with these inequalities, then you get a bound on the sphere packing density. And this theorem doesn't tell you anything about where you get the function. All it says is if you have the function, then you learn an upper bound for sphere packing. So let me prove this theorem to you. We've got 6 minutes, which is more than enough time to prove this for Bravais lattices. So let's prove this for Bravais lattices. The theorem is by no means limited to Bravais lattices. The theorem works for all sphere packings. The proof, once you do Bravais lattices, it's not much harder to do it in general. Basically, I'll do a 1 blackboard proof for Bravais lattices. If you do a 2 blackboard proof, you can do it for general sphere packings, but no point in trying to cram that in here. So let's imagine we've got a Bravais lattice lambda in Rn. Let's imagine that it's got minimal vector length 2. In other words, it's a packing with unit spheres. The thing is, without loss of generality, we can scale it to whatever radius we want. So let's imagine we've got this. So the way the proof technique is going to work is basically we're going to take Poisson summation and plug things in. So what do we know from Poisson summation? We know the sum of our magic auxiliary function f over the lattice is equal to 1 over the volume of a fundamental cell times the sum over the dual lattice of f hat. And now, basically, all we're going to do is try to extract information from this by doing inequalities on both sides. The question is, how do you extract information from an identity like this? If somebody tells you two things are equal, the way you learn as much as possible is by making the two sides as different as you can. So here, one way to make them different is to try to make as many of the terms here as possible be non-positive, and as many of the terms here as possible be non-negative. The more different you can make the two sides look, the more you'll learn from the fact that they're secretly equal after all. So here, we've got a lower bound where we throw away every term except the origin. So what we find is this thing, whatever it is, it's greater than or equal to f of hat of 0 over v. On this side, we say, well, because we have minimal vector length 2, every point in lambda except the origin is in the f is non-positive region. So the left side is bounded above by f of 0. So what do we conclude? We conclude that 1 over the volume of a fundamental cell is bounded by f of 0 over f hat of 0. But what's the density? Remember, the density of our packing is equal to the volume of a sphere divided by the volume of a fundamental cell. So the density is pi to the n over 2 over n over 2 factorial times 1 over v. So the density satisfies the inequality we want. So in the remaining 2 minutes, let me say 3 or 4 things. One is, this might look like the world's stupidest proof technique. The thing is, what we did was we took a deep, wonderful duality and we sort of wantonly threw away all the non-trivial terms on both sides. And why is that even a remotely reasonable thing to do? So there are sort of 3 things I can say. One is we have no choice. The thing is, who knows where the other terms are? They're at lattice points of lambda or lambda star. We don't know anything about these lattices. These terms could be anywhere. We're throwing away the terms we don't know and keeping the ones we do. So first of all, we have no choice. What else are we going to do? Secondly, we can hope that if f and f hat are decaying fast enough, that maybe the terms we threw away are not very big, and so we might not lose much in this. And third, we might hope to get really lucky. The best case scenario is, what if all the terms we threw away were 0 to start with? If we only threw away zeros, we would not lose anything in this bound, and then we would get an exact bound for density. And that's what happens in 8 and 24 dimensions. In 8 and 24 dimensions, you can find a magic function f with the property that when you plug it in for the optimal lattice, all the terms you're throwing away are already 0, and you get an exact upper bound for density. So what I haven't told you is where the auxiliary function f comes from. I've told you, what properties it should have, what density bound you get, and why it works, at least for Bravais lattices. But I haven't told you where to find it. And the answer is we don't know. So a problem that humanity really ought to be able to solve is, given a dimension n, what's the best function f? How do you choose f in order to minimize this bound? So that's a convex optimization problem. It's in fact an infinite dimensional linear programming problem. This seems like the sort of thing humanity ought to be able to solve. But so far, the only dimensions that we can solve this in are 1, 8, and 24. So in general, all we can do is numerically approximate this. What you can do is sort of, guess some class of functions f that's pretty flexible, say polynomials times Gaussians or something, and try numerically optimizing it, hoping that it will at least approximate the optimal function. So you can numerically compute the answer to this, we just don't know how to get it exactly. So basically, I said that Noam and I proved this. We proved it a little bit earlier than 2003, but in any case, let's say 14 years ago. So the question is, why did it take until last year for Vyazovska to solve the problem in 8 dimensions? So basically, this was an incredibly frustrating situation. We could numerically compute this bound. The bound seemed to give a sharp, exact answer in 8 and 24 dimensions. We could compute it to 50 decimal places. It agreed with the actual density to 50 decimal places. There was no way this was just a coincidence. On the other hand, we couldn't prove they were exactly equal. And the problem is we couldn't find the right function to plug into this bound. So what Vyazovska did is realize that if you put this in the right context in number theory, you can construct the optimal function using something called modular forms. And that's really a totally different story that we don't have time for today. But basically, the sort of one-sentence summary is number theory to the rescue. So basically, I've described this in ways that are fairly different from the pair correlation function structure factor picture, but that's secretly what's happening here. The thing is, if you think about this, what is this sum over lattice points doing? That what you're doing is, if you have a radial function f that depends only on the distance to the origin, you're basically summing this according to the pair correlation function. And then you're doing a Fourier transform here. So basically, if you work this out, it really amounts to what I described earlier, but I think we're about out of time here. In any case, the sort of overall summary is we've got this technique for bounding packings. It works surprisingly well, doing things like solving 8 and 24 dimensions if you choose the right function f. And it gives good asymptotic bounds. We don't know how to optimize it in general. And the other thing is this can't be the right answer. Because remember this picture I described with the pair correlation function, that basically everything we're doing here is secretly depending only on pair correlations. And I can't believe that pair correlations really know everything there is to know about a packing, except in miracle cases like 8 and 24 dimensions. In general, you really need to take into account higher order correlation functions somehow. And I don't know how to do that, but somebody ought to do it. In any case, there's this framework of semi-definite programming bounds that ought to work here, but nobody's been able to get it to work out. In any case, I should stop taking up time so that we've got the break, but I'm happy to chat more about this with anybody who's interested afterwards.